Let's generalize some of the concepts we learned in the last video to solids that have a hollow component. Let's imagine that we have a region between two functions in two dimensions, and we want to rotate that region around an axis. So a picture of this, we have some outer function, capital R of x, and then we have some smaller function, small r of x, and we want to rotate from A to B. If we imagine rotating this region about the x-axis, we would have a solid component that gets rotated around, and then the inside here would be hollow. So we have a hollow region here. How do we find the volume only of the solid part that's been rotated? Well, the way to do it is to find the volume of the smaller section, the whole, if you will, and then subtract out the volume of the whole from the volume of the entire thing. So if we could find the volume of the entire solid, that's from the function capital R, and then subtract out the volume from the function small r, that gives us the volume only of the section that we're interested in. All right, take a look at this formula. We have the outer volume, capital R, subtracting the inner volume, small r. When we subtract in this way, we subtract out the volume of the whole, and we only have the volume left of the exterior that we wanted. So this formula here describes the volume of a solid that has some hollow region. Let's practice using this formula. Take a look at example 3. We want to find the volume of the solid formed by rotating the region enclosed by these two curves, and we're going to imagine rotating it around several different places, the x-axis, the line y equals 1, and then the y-axis. Let's take a look. Once again, the first thing to do here is to draw the region. So we have x squared, and then we also have the function square root of x. And the first part of this problem will be to rotate this region around the x-axis. Now, what region are we talking about? Well, the region is bounded by these two curves. It's this leaf-shaped region here. We're imagining taking that area and rotating it first around the x-axis. I have trouble visualizing this in 2 dimensions, so let's take a look at a 3-dimensional plot. So here we have our 2-dimensional region bounded by the curves x squared and square root of x, and this is the bounded region. We will take that leaf shape and rotate it around the x-axis. The shape that we get, the solid, looks something like this. The exterior looks sort of like the nose cone of a rocket, and the interior, well, it kind of reminds me of one of those coin traps that you see in malls where you drop your quarter and it slowly goes around and around and around and around, and then just before it gets to the center you grab it and make sure that it doesn't get lost forever. But it looks sort of like one of those black hole coin traps. So that's the solid. We're interested in finding the volume, but we don't want the volume of the hollow section here. We only want the volume of this shape that's been spun around, this leaf shape as it spins around. What's the volume inside that? That's what we're going to solve with this problem. Incidentally, in the next part of the problem, we will take the same region, but instead of spinning it around the x-axis like this, we will spin it around the line y equals 1. When we do that, the shape looks like this. And it looks almost the same. But if you notice, this shape has a sharp nose. There's a point at the end of the nose cone. And when we rotate around the x-axis, you'll notice that the point is smooth. There's no sharp point there. So the two solids are actually different, and they have different volumes. Now that we have a better idea of what this 3-dimensional solid looks like, let's figure out how to find its volume. We need to find the region bounded by these curves, and we have the curves, but one thing that we don't have is limits of integration. We need to know what do we integrate to and from in order to find the volume. In fact, what we need are these intersection points. We need to know where these curves cross. So to find the intersection points, I set the two curves equal to each other and solve for x. So I set these two curves equal to each other and I solve for x. Well, if I square both sides, I get x equals x to the 4th, and then x to the 4th minus x equals 0. Factor out an x cubed minus 1 equals 0. So either x equals 0 or x cubed minus 1 equals 0. Well, x cubed equals 1. I can take the cubed root of both sides, and because it's an odd root, I don't do plus and minus. I simply get x equals 1. So here are my two solutions, x equals 0, x equals 1. Those are the intersection points of these two curves. And we will use those as our limits of integration. So here's x equals 1, here's x equals 0. All right, to find the volume of this two-dimensional region, rotated again about the x-axis, I need an expression for the outer radius. The outer radius is the distance from the line of rotation, which is the x-axis, to the outside of the shape. This expression here is my outer radius. The inner radius is the distance from the inside of the shape to the line of rotation. So in this case, capital R is the square root of x, and small r is x squared. So now I can use these in my volume formula. Volume equals pi times the integral from 0 to 1. First I have capital R of x, quantity squared, minus small r of x, quantity squared, dx. For this problem, we will leave the integral just like this. We could continue to solve. We'd get powers of x here, and we could use antiderivatives and fundamental theorem of calculus to find the actual volume here, but we'll leave the problem here. Our main point for this example was to set up the volume expression, and then we could use integration to find the numerical value. So this is our answer for part A. Let's take a look at part B. For part B, we're rotating this shape not around the x-axis, but around the line y equals 1. This is something new. We have not seen how to rotate around a line other than the x-axis. So if we want to rotate around the line y equals 1, that's right here. Notice that if you plug in x equals 1 into either of these functions, you get y equals 1. So this is our line y equals 1. And now we want to rotate around this line. Well, when we do that, we have different expressions for the outer radius and the inner radius. Now, the outer radius is this right here. And we need an expression for that. And the inner radius is now right here. How do we deal with this? Well, let's go back to the front of the handout. We can extend these concepts of rotating a certain region about the x-axis to rotate about the y-axis, for instance. Or we could imagine rotating around any vertical or horizontal line. The key here is to find an expression for the radius of the solid. And something that's very important is to think of the radius as an expression that describes the distance from the line of rotation to the extent of the two-dimensional region. So when we think of a radius function, either capital R or small r, we want to think of the distance from that function to the line of rotation, whether that's the x-axis, whether it's the y-axis, or whether it's some other horizontal or vertical line. So the key here is to think of the distance from the line of rotation to the outside of the shape. Let's use that concept for this example. So we are rotating our two-dimensional region now around the line y equals 1. Our radius functions are going to be different. So let's get rid of these. Now the outer radius is this distance here. It's the distance from the line of rotation to the outside of the shape. That is the outer radius. How do we find that? Well, it involves the function x squared, but it's not equal to the function x squared because x squared is this distance here. So how do we find this outer radius, capital R? Well, this distance is always 1. And notice that capital R plus this distance equals the total distance of 1. So I'm going to set up a relationship here. For part B, capital R, if I add this height here, this is the y value x squared. So if I add x squared, the outer radius capital R together with x squared make up the entire distance 1. So capital R plus x squared equals 1. This is the most difficult part of the problem here. If we can understand how to obtain expressions for the radii, then we can solve these problems. Let's practice with the small radius, small r of x. So the small radius is the distance from the line of rotation to the inside of the shape, that's small r. And in the picture, it's this distance here. It's going to involve the function square root of x, but it's not equal to square root of x. This distance here is square root of x for any x value. So if we take the square root of x distance and add it to the distance of small r, that makes the total of 1. So we have a relationship here. Small r plus square root of x equals 1. Once again, this is the trickiest part of the problem here. If we can solve the outer radius and the inner radius, we can work through any of these problems. Once we have these expressions, we can solve for capital R and small r, and then just plug them into the volume formula. So from the first expression, the outer radius, capital R, is 1 minus x squared. And from the second expression, the inner radius, small r, is 1 minus the square root of x. So the volume expression for part B is pi times the integral from 0 to 1, and now capital R is 1 minus x squared, so we square that, minus small r, which is 1 minus the square root of x squared. If we evaluate this integral, we will get a different value than the first one because we are rotating around a different line. Once again, we'll skip the steps of evaluating the integral here. I highly encourage you to work through the steps on your own, expand out these squares, take the antiderivative, use the fundamental theorem of calculus, and you'll see that the answer that you get from part B is different from part A. Let's work through the last part of example 3. Let's take the same region, but now let's rotate around a vertical line, the y-axis. Once again, we're taking the region bounded by the curves y equals x squared and y equals square root of x, but now we rotate around the y-axis. In order to do this, the integral will be in terms of y. So the volume integral will look like pi times the integral from a to b, but my functions here will be y functions in terms of y. The reason we need to integrate with respect to y instead of x is that rather than take vertical cross sections rotated around a horizontal line, we are now taking horizontal cross sections rotated around a vertical line. We will find a representative expression for a horizontal slice rotated around the y-axis, and then in order to find the volume of all these slices, we need to integrate from a lower y value a to a higher y value b. So instead of integrating along the x-axis, we integrate along the y-axis. We integrate with respect to y. So when we think of the distance capital R, this radius, that will now be a horizontal distance. Here is capital R. And this will be in terms of y. Well, how do we obtain this expression? This function is y equals x squared. So capital R of y, in this case, is a distance along the x-axis. This is some x distance. But I need to express this x distance in terms of y. I can do that by solving the y equals x squared for x. So I take my function y equals x squared, take the square root of both sides. Ordinarily, I would use plus and minus, but I'm only using positive y values. So I have x equals the square root of y. That is the y distance. Now, let's think of small r. That's the distance from the line of rotation to the inside of the shape. This would be small r of y. This involves the function y equals square root of x. But this small r of y is an x distance. It's some distance in the x direction. How are x and y related for this curve? Well, y equals square root of x. So I take that expression and solve for x. Y equals square root of x, square both sides, and I have x equals y squared. This x corresponds to the x distance, but I can express it as a function of y. It's equal to y squared. So this inner radius as a function of y can be written as y squared. So I have my outer radius, square root of y, my inner radius, y squared. How do I obtain the limits of integration? That's the last part here. Well, the limits of integration will be y values. I start integrating at y equals 0, and I continue till I get to the upper edge of the figure. This will be when x equals 1 and also when y equals 1. So my y limits of integration are from a equals 0 to b equals 1. These limits, once again, are on the y-axis, not along the x-axis. So in this case, the volume is the integral from 0 to 1. Capital R is the square root. Small r is y squared dy. Once again, we'll leave the integral here, but I encourage you to work through the steps of expanding that out, finding antiderivatives, using the fundamental theorem of calculus, and you will get the volume of this two-dimensional region rotated around the y-axis. Let's work through example 4. Find the volume of the solid formed by rotating the region enclosed by these curves and the y-axis about the line y equals 3. Once again, we first need to sketch the two-dimensional region. So we have y equals x squared, y equals 2 minus x. Y equals 2 minus x is a line with a slope of -1 and a y-intercept of 2. So it will look something like this. This is y equals 2 minus x. And we have the region enclosed by these curves and the y-axis. So this is our region. It's almost a triangular shape with a curved edge here. We are taking this region and we are rotating around the line y equals 3. Well, this line has a y-intercept of 2, so y equals 3 is about here. This is the line of rotation. We are rotating around this horizontal line. We have a hollow section here. If we can imagine taking this two-dimensional region and rotating around this line, we have a hollow component over in here. And so we need to use the volume formula for 2 radii. Since we're rotating around a horizontal line, we use x as our variable for integration. So the volume formula will be pi times the integral from a to b, capital R of x squared minus small r squared dx. We need expressions for capital R and small r. Let's think of drawing those in. Once again, the key for the radius expressions is to find the distance from the line of rotation to the outside of the shape or to the inside of the shape. Let's focus on capital R first. Capital R of x is this distance here, the distance from the line of rotation to the outside of the shape. That is capital R. Now we can imagine that capital R is going to involve this curve x squared. But is capital R equal to x squared? Well, no, x squared is this distance here. So if we can imagine taking capital R and then adding x squared, maybe it's a bit easier to imagine somewhere over here. If this is capital R and this is x squared, when we add those together, we get the total distance, which is 3. So capital R plus x squared must equal 3. Now I can solve for capital R of x. This is 3 minus x squared. How about the small radius, small r of x? That's this distance here. Well, this is going to involve the line 2 minus x, but it's not equal to 2 minus x. 2 minus x gives us the y values from the x-axis. So if I take the y value here and add it to small r, I get the total distance of 3. The y value is 2 minus x, so I have this expression for small r plus 2 minus x equals the total distance 3. Solving for small r, I have 3 minus 2 minus x. So this is negative negative x, which is just x. 3 minus 2 is 1. This is x plus 1. So I have my expression for the outer radius and for the inner radius. Once I have those, I can plug them into the volume formula. There's one other component that's needed here. I need the limits of integration. I'm starting at a equals 0. So this is one limit when a equals 0. Starting here, I will add up volume until I get to this point right here. What is this x value? How do I find that intersection point? Well, I take the two curves and set them equal to each other. So for the intersection point, I set the two curves equal. One of the curves is x squared, the other is 2 minus x. So x squared equals 2 minus x. I want to move everything to one side and set this equal to 0. X squared plus x minus 2 equals 0. This factors as x plus 2 times x minus 1. So I obtain solutions of either x equals negative 2 or x equals positive 1. Positive 1 is the x value of this intersection point here. This is x equals 1. And if we think of plugging in 1 into the functions, the first y value would give us 1 squared, which is 1. The other y value, 2 minus 1, also a y value of 1. That's the y value of that point. So now that I have my limits of integration and the functions, I can set up the integral. This is pi times the integral from 0 to 1. Capital R is 3 minus x squared. Capital R squared minus small r, x plus 1, squared dx. Once again, we're not so interested in solving this integral. If we expand everything out here, we'd simply have a polynomial. We are more interested in determining how to set up the volume integral from the information that's given. Let's work through one more example of a rotated solid. Consider the region bounded by the graphs of e to the x equals 1, and the x and y axes. And let's imagine rotating this two-dimensional region about the x-axis and about the y-axis. Once again, we first need to draw a sketch of this region. So we have the line x equals 1, and we have the function y equals e to the x. We want to rotate this region, bounded by these curves, about the x-axis and then about the y-axis. First, let's do part A. Let's rotate around the x-axis. When we rotate around the x-axis, notice that we don't have any hollow region here. This is a solid that's being rotated around. It looks like kind of a lamp shape. If we were to imagine rotating this around the x-axis, we would have this lamp-shaped solid, and there's no hollow component. So here, we use the volume formula for just a single radius. Volume equals pi times the integral from a to b of the radius squared dx. The radius here, once again, is the distance from the line of rotation to the outside of the shape. That's this y distance. But this y distance is equal to e to the x. So our radius function r is just e to the x. So we have pi times the integral of e to the x squared dx. And we are integrating starting at x equals 0 and adding up these slices until we get to x equals 1. So the limits of integration are from 0 to 1. Let's go ahead and work through this one quickly, just because it's a fairly simple integral and it's good practice. When we have e to the x squared, that equals e to the 2x. So we have pi times the integral of e to the 2x from 0 to 1. The antiderivative of e to the 2x is e to the 2x divided by 2. This is one of those rather simple substitution problems where we need to sort of guess and check what the antiderivative is. If we take the derivative of e to the 2x over 2, well, the derivative of e to the 2x is e to the 2x times the derivative of 2x. So we'd have an additional times 2. Those would cancel. And yes, indeed, the derivative of e to the 2x over 2 is e to the 2x. So here's our antiderivative. We plug in 1, we plug in 0, and see what we get. We have pi times e to the 2 times 1 is e to the 2 over 2 minus e to the 0. E to the 0 is 1. So 1 over 2, put these in parentheses. This is our answer, rotating around the x-axis. Now what happens if we want to rotate around the y-axis? If we rotate around the y-axis, the integrals will be in terms of y instead of x. But in this case, think of what would happen if we rotated around the y-axis. Part of the shape would have a hollow component. We're taking all of this region here and we're rotating it around the y-axis. So for this part of the shape, there's no hollow component. It's solid. But for this part of the shape, we have a hollow region here when we rotate around the y-axis. So to approach this problem, we first need to divide this into two regions. This is going to be on a case-by-case basis. Let's call this first one V1, and let's call this next one V2. So in order to find the total volume, I want the volumes of both of these regions rotated around the y-axis. Let's focus on V1 first of all. V1, the formula is pi times the integral from a to b. This is in terms of y now, so r of y squared dy. What is the radius for this first region here? Well, the radius is the distance from the line of rotation, which is now the y-axis, to the outside of the shape, which is this x equals 1. This is always a constant distance of 1. So for V1, the radius is simply 1. That's this distance here. So for the first volume, we have pi times the integral. What are the limits of integration? Well, we're integrating along the y-axis. We're integrating from smaller values up to larger values. So for V1, we're integrating from this value to this value. We need to determine where this function crosses the y-axis. Well, when x equals 0, y equals 1. Plug in 0 into the function, and we have e to the 0, that's 1. That is the y value at 0. So this y value here is y equals 1. So for the integral, we integrate from 0, vertically adding up volumes until we get to 1. So the limits of integration will be from 0 to 1. The radius is this distance here, which is simply 1. So we integrate 1 squared dy. How about volume 2? Volume 2 has a hollow component when we rotate around the y-axis. So we will have an outer radius here, and we will also have an inner radius. Let's first think about the outer radius. The outer radius is the distance from the line of rotation, which is the y-axis, to the outside of the shape. This is the outer radius. That outer radius stays constant. It's always the distance from the outside of the shape to the y-axis. Well, that's just a distance of 1. So the outer radius is simply 1. How about the inner radius? That's this distance here. This is some distance along the x-axis. So I could call this x, but I want an expression in terms of y. So how do I correlate y and x for this distance here? Well, I'm going to use the function y equals e to the x. So I'll start by just calling this distance x. But what I really need is an expression for the inner radius in terms of y. So instead of using x as the variable here, I want to figure out what is x in terms of y. Well, if y equals e to the x, that means that x equals the natural log of y. I can take the natural log of both sides here, natural log of y and natural log of e to the x. Well, the natural log of e to the x is simply x. So my small radius here, small r, it's an x distance, but I want to express it in terms of y. It is the natural log of y. So I have my inner radius, I have my outer radius. Now I can set up the integral for this second volume. So for V2, the formula is pi times the integral from a to b, capital R of y squared minus small r of y squared dy. Capital R of y was just 1, so 1 squared minus small r of y, which is natural log of y. So we subtract natural log of y squared dy. What about the limits of integration? What do I use for a and b? Well, now I'm adding up area starting at this y value and continuing until I get to the y value of the intersection point. What is the y value of that intersection point? Well, that's the y value when x equals 1. If x equals 1, what is y? Y is simply e. So this height, this b value for the integral, is e to the 1 or just e. So for this second integral, I integrate from a y value of 1 to a y value of e. That will take all of this volume, adding up volumes of horizontal slices, moving upward from a y value of 1 to a y value of e. So the total volume, if we rotate around the y-axis, would be the sum of these two integrals. So for part B, the answer is total volume equals the volume from V1 plus the volume from V2. Pi times the integral from 1 to e, etc. This is the answer for rotating around the y-axis.